All right, Bosco. Then I'm gonna stop sharing, and I'm gonna let you take it away. This is for our Ultrasonics with a perspective on design. Go ahead, Bosco.
Thanks, Ray.
You're welcome.
I hope you can see the screen.
Yes.
Okay, very good. So this is a continuation of the ultrasonic welding seminar. This morning we did fundamentals of ultrasonic welding, and this afternoon we'll be talking about ultrasonic part design. And sorry for the delay, everybody, but we'll get started right away here. So the two main areas that we'll be talking about today are materials and joint design. More specifically, materials, which materials can be welded, and we'll also be talking about material compatibility. In the joint design section, we'll talk about the principles of a joint design, proven designs that we know historically have worked, and also talk about some problematic designs that we've seen as well, and how does the material influence the joining process. So obviously we're talking about welding of plastics, and plastics can be divided up into several general or broad categories. Thermoplastic materials are materials that can be reshaped through heat, and these materials can easily be welded. Thermoplastic elastomers, on the other hand, can be remolded through heat, but they oftentimes have, excuse me, rubber properties. And it's this softer composition that thermoplastic elastomers have that makes them rather difficult for welding. Thermosets, on the other hand, they cure through a chemical reaction, and so therefore, once they have been cured, they cannot be welded. Composites, rubbers, those kinds of things that go through a chemical reaction for their curing process, once they've been gotten to their finalized state, adding heat to them will not cause them to go back into a liquid form. And furthermore, homogeneous welding is only possible between parts made of identical plastics. So we're talking about welding ABS to ABS or ABS to acrylic. However, with the case of ABS and acrylic, there is compatibility between them, as well as ABS with polycarbonate. And then with some limitations, polycarbonate with acrylic and polystyrene with polyphenylene oxide or PPO. This really depends on the melt flow index and the processing temperature of the materials. And we'll be getting into that a little bit further later. If we take thermoplastic resins and then further subdivide them into two broad categories, we have semi-crystalline thermoplastics as well as amorphous thermoplastics. Semi-crystalline thermoplastics have simple chemical molecular chains, and they arrange themselves in a crystalline matter. The remaining sections are amorphous, but the molecules are long to complete the crystallization. Semi-crystalline materials are typically more difficult to bond. They have a very sharp melting temperature, a state at which they go from solid to liquid. But on the other hand, amorphous thermoplastics are easier to weld. Their chemical composition and the molecules are not arranged as regularly as you would see in a semi-crystalline material. So therefore, those polymer chains can be broken more easily and then rejoined to create the bond. So furthermore, semi-crystalline materials, as I've mentioned, have a very clear defined melting point, somewhat like water, that below 32 degrees is solid, above 32 degrees it's liquid, and then when we reach the boiling point of water, it changes state again. But semi-crystalline materials typically have a very low molecular weight. They become liquid very quickly. They make that sharp transition from solid to liquid very quickly. We can often identify semi-crystalline materials by the sound that they make when they're dropped on the table. So for example, if you were to think of a milk jug, an empty milk jug, and if you kind of drop that on a table, you'll hear a hollow sound or kind of a thud. That's one way to identify a semi-crystalline material. They typically have higher amplitude requirements. So in 35 kilohertz, we're talking about 0 to peak amplitudes in the range of 25 to 35 microns. Or in 20 kilohertz, we're looking at amplitude ranges from 30 to 45 microns. And for semi-crystalline materials, we typically limit them to a near-field weld. And what I mean by that is the distance between where the sonotrode contacts the part and where the driven part contacts the stationary part. This distance should be 4 millimeters or less. In some instances, with amorphous resins in particular, this far field welding, or a distance of more than 4 millimeters, can be realized or can be obtained. But for semi-crystalline materials, we specifically want to concentrate on near field welding. Amorphous thermoplastics do not have a defined melting point. They have what's called a glass transition point, that as you add heat, they become gradually softer, softer, softer until they become liquid. So like ice cream or like candle wax, if you see the flame on a candle, directly next to the flame, you'll see liquid wax a little bit further outside of that. It'll be soft. You can kind of poke at it with your finger, but the rest of the candlestick further and further away from the heat source, the flame, that will remain solid. So amorphous thermoplastics typically have a metallic ringing sound. So if you took an amorphous part and dropped it on a table, you would hear that ringing sound. Again, just a way to identify an amorphous over a semi-crystalline material. And as you can see, they typically have lower amplitude requirements. In 35 kilohertz, the range is about 10 to 25 microns of 0 to peak. And in 20 kilohertz, the range is about 15 to 30 microns. So here, if we overlay the melt characteristics of the two materials, you can see the red line, amorphous resins, that when they reach that glass transition point, they continue to gradually soften and then eventually become liquid. Whereas the blue line, the semi-crystalline line, the material doesn't soften, but rather it very sharply and very quickly melts when it reaches that melt temperature. So when we think about the energy director, or the area that is intended to melt and cause the bond in a semi-crystalline material, because it becomes liquid very quickly, the joining velocity can also change, and therefore that molten material, instead of being contained within the area to be welded, it can very quickly spread and move out of the joint area, and therefore create a weak bond. So for that reason, primarily, semi-crystalline materials are more difficult for bonding. It's not to say that they can't be bonded, but again, we just have to take special precautions and different parameters that we would normally use to get them to bond. So to further expand on some of the characteristics of those types of materials and materials in general, we typically look for the stiffness in a material. So the stiffer the material is, the more easily it is for welding. So the higher the Young's modulus or the flexural modulus is in a particular material, usually the easier it is to weld. And these numbers can typically be found on the material data sheet of your material. Density as well. The denser the material is, again, the stiffer it typically becomes. Higher density values typically are exhibited in amorphous resins, and again, they are easier to weld. When we talk about the melt flow index or the melt flow rate, this is again a standard test that you can find a number for within the material data sheet, and a lower value is better. These values typically range from about 4 grams per 10 minutes up to 30 grams per 10 minutes. And this gets back to what I was talking about earlier, that in a semi-crystalline material, when it changes from solid to liquid, when it does that very quickly and flows very easily, it's hard to contain the molten material within the joint area. So having a lower melt flow index means that the material is more like honey or syrup rather than like water. So when it's in that lower melt flow rate number, that means the viscosity is such that it's like syrup or honey, and when it is contained, then therefore the bond that's created is much better because the melt is contained. And then finally, melt temperature. The lower the value, the better, which typically means lower amplitude requirements. So heat and amplitude are analogous terms, so we will sometimes use those interchangeably. So having a lower melt temperature means that amplitude requirements are typically lower as well. And just another point about melt flow index and melt temperature, when we look at compatibility of materials, these are the two numbers that we look at, the melt flow index and the melt temperature. So if you have two similar materials that number one, first have to be chemically compatible, but when we talk about ABS and acrylic being bonded together, we also have to look at the melt flow rate and melt temperature. The melt flow rate should be within 10% of one another, and the melt temperature should be within 50 degrees of one another. This can change depending on the grade of material that's used. So if you have a ABS, for example, that's extrusion grade, and a ABS that is injection molding grade, they may have very similar melt temperatures, but they may have properties that change their melt flow rate. So even though they may be both have a base resin of ABS, again, the melt flow rate and the processing temperature need to be in a similar range to get that true homogeneous bond that we're looking for. Here are some amplitude requirements for specific materials. These half dozen or so materials are the most common, the most typical that we see. And you can see that things like nylon, which is a semi-crystalline material, has a higher amplitude requirement than, for example, ABS down at the bottom of the chart, which has a much lower amplitude requirement. So depending on the material that you choose, again, primarily we adjust the amplitude depending on the material. Another consideration for your plastic parts is environmental conditions such as humidity. Some materials are what is known as hygroscopic, meaning that they can absorb moisture, especially nylon. So if a material is not dried properly before molding, or the molded plastic part is not stored properly after molding, then the ultrasonic welding process can be inhibited. Water or moisture within the parts requires that the moisture be sort of boiled away, if you will, before the welding happens. So for that reason, if there are parts that you're welding that are hygroscopic, please pay particular attention to handling them properly, sealing them in a plastic bag, or maybe even packing them with a desiccant inside so that any moisture is inhibited from getting into the plastic parts. Additionally, additives, fillers, and surface finishes can also affect weld quality. When we talk about additives, we're talking about things such as UV stabilizers, flame inhibitors, lubricants, or internal release agents. The more filler or additive that there is within a plastic part, the less weldable, meltable material, base resin, in other words, that we have. And additionally, lubricants by their nature are intended to reduce the surface friction of a part when it comes out of the mold. For example, if you do have internal release agents or lubricants within the part, then this will significantly affect the weldability of the materials. A lot of times what we see is silicone valves or valves that have some sort of lubricant in them. Please pay particular attention to containing that lubricant and not getting it into the weld area, because it will be a weld inhibitor. Oftentimes, fillers such as glass fibers, glass spheres, or carbon fibers are added into a material to enhance the mechanical properties, the stiffness or the strength of the material. While on one hand, stiffening the material does certainly create better transmission of the mechanical vibrations, it, on the other hand, does reduce the amount of weldable material-based resin that's within the parts. That's not to say that we can't weld parts that have glass fiber or glass fill in them. We've very successfully welded parts that have up to 30% glass. The downside is that the glass can cause wear to the tooling. So when the sonotrode is making contact with a glass-filled part, it will very often wear much quicker than contacting a non-filled part. The other downside is that the glass fibers, which are intended to strengthen the properties of the material, do not bridge across the weld area. They're usually very large, and they don't intermingle like they would in the molding process. So therefore, the joint or the weld area often does not have the same strength properties that you would see in the rest of the part. So in those instances, what we recommend is that the weld be up to or more than 1.5 times nominal wall thickness. So you make the joint larger in order to compensate for those strength deficiencies that you might see in the joint area. And then finally, surface finishes. If you have a chrome plated or metallized part, or if you have a painted part, we see this often in automotive applications. That coating or that surface finish, the metallizing or the paint, becomes a contaminant or a weld inhibitor. So for those areas that you intend to weld to a metallized or a painted surface, either they should be masked off prior to the surface finish being applied, or the surface finish may have to be removed prior to welding. Depending on the thickness of that surface finish, we may be able to break through that surface finish, but best practice would be to eliminate it in the welding area or remove it as needed. So let's talk now a little bit about some variability that you might see in the mold. Best practice would be to have a single cavity mold for the upper part and a single cavity mold for the lower part. However, in high volume manufacturing, you often have to mold parts in multi-cavity molds. So something to consider is the dimensional accuracy within each mold cavity. We do see slight variations, especially if runner or gate balancing is not done properly. Some parts may have higher density, be packed out within the cavity more than other areas in the mold. So keep that in mind. But then as the part cools, any sort of warping or distortion and design flaws such as sink marks can also affect the weldability of the part as well. And as we mentioned before, drying material, making sure that there's no moisture or other environmental conditions in the parts, that's also important to consider as well. A trend that we've seen recently is for, especially in medical device handles that are used for minimally invasive surgeries, laparoscopic or endoscopic surgeries. Those handles are now molded in two-color or over-molded with a soft touch over the handle. This can be a challenge for us. We do accomplish those sorts of welds fairly regularly, but it's just necessary that we have access to the joint design directly underneath where the sonotrode would contact. And I've got the mouse here up on the part, and as you can see, keeping the overmolding to a minimum, and especially not in the area directly above the welding joint. In the other case where the overmolding wraps around a larger area, we would have to make contact with the overmolded or soft material, which would typically dampen the vibrations and therefore inhibit the transmission of those vibrations to the energy director. So something to keep in mind, that if you have multi-component parts or parts that do have an overmold on them, that access to the welding area should not be inhibited. Okay, so next section will be on basic design rules for ultrasonic welding. So what we mean is, how do you properly design the parts so that you maximize the ability for them to weld properly? And we've come up with these 7 points, and I'll go over each of them. But this is an ideal situation, and sometimes the wall thickness that's required for some of these weld joints may not be achievable, but as many of these 7 points as you can ensure the design into your plastic parts, the better off the success of the project will be. So number 1 is having an energy director, defining a place to start the weld. So what we're talking about is a detail, and we call it a sacrificial bead. So this bead melts and flows and bonds, and hopefully will bond onto more than just the horizontal surface, that the volume of melt that's calculated will not just weld into the horizontal surface here, but will also bond onto the vertical surfaces. So that'll give you some mechanical advantages, as well as making the part leak free. Again, the name of the game is to reduce the surface area. So the intent of the energy director is that it be as sharp as possible, and that it minimize the surface area between the two parts to initiate the melt. Secondly, sonotrode contact, having direct access or direct vertical contact above the weld joint. This can sometimes be a little bit more difficult if you have a round part, or as I showed earlier, a part that might have an overmold in that area. But allowing the sonotrode to make contact directly above the weld joint is of utmost importance. Number 3, support. So the blue part, when loaded into the fixture, should remain motionless. Very often we have to apply relatively high forces in order to get the transfer of the mechanical vibration into the parts. And if the part in the fixture either is loose or moves or is not properly supported, and it's allowed to deflect, then we may get inconsistent welding results. Number 4, melt encapsulation. So again, calculating the volume of melt that's created by the energy director, that it stays contained within this in this tongue portion of the blue part. Number 5, centering. If you aren't able to fully encapsulate in this tongue and groove formation, if you only have a step joint, Making sure that the parts stay centered, that they don't essentially fall off during the welding process is very important. Volume and part travel, allowing the part to move freely and the melt to go somewhere. So sometimes what we see is that parts are designed in a way that they press fit together, and this is not desirable. So there should be enough of a gap in between the parts here, such that if you did load them together and turn them upside down, they would fall apart. Again, what we're looking for is the red part to be driven by the sonotrode, to vibrate freely, and the blue part to be held in the fixture motionless. If the parts already have a bit of a press fit in that situation, and the blue part will resonate together with the red part, then we're not creating relative motion between the parts, and this is a weld inhibitor. And then finally, preventing a hard stop. We'll often see either a cosmetic gap or a bit of a gap in between the finished parts. We don't want to rely on the welding to stop when the red part contacts the blue part. We want the welder to do the work. So the welder has controls such as an encoder, and we can monitor the energy and power that's put into the part. And those controls are more reliable in stopping the welding process than relying on the parts to quote unquote bottom out. So again, the energy director should be the weakest point. This is the part that will take the most deformation. It should be, again, sharp, and the heat generated will be localized and focused on that point. So this little video depicts that with the application of force. So you can see that the deformation is happening right at the point of contact and not as much at the top or the bottom of the part. And so furthermore, an energy director is absolutely required. If we had a situation like over here on the right, where the energy director is missing or lacking, the entire surface of the part typically is where the heat affected zone goes to, and that's undesirable. We want to focus the heat, like shown in the middle graphic here, that the heat affected zone is only within where the weld is supposed to happen, not heating the rest of the part or further away from the joint. A question that often comes up is how large should the energy director be? Typically, there are two recommended angles for energy directors, and we'll only talk about the typical 90-degree. This is the proven angle that we will recommend to our customers more often than not. But depending on size constraints, wall thicknesses, those kind of things, we may see a 60-degree angle at some point as well. And that's okay. You just may have to make the energy director a little bit taller if the angle can't be achieved at 90 degrees. And then the height of the energy director is primarily tied to the size of the part. And I mean, although there's not a clear definition of what a small part is or what a large part is, use your judgment there. In a small part, we'll see energy directors in the range of 0.3 to 0.4 inches for amorphous resins. And for a small part for semi-crystalline resins, we'll usually see a little bit larger of an energy director, 0.5 to 0.7. And then large parts, amorphous resins, 0.5 to 0.7 millimeters, or as large as 1 millimeter for large semi-crystalline parts. And then the sharpness of the energy director is often called into question. Our recommendation is to make it as sharp as you can. The mold makers will often say that they can't get a perfectly sharp energy director, but as sharp as you can get it is ideal. And then another criteria that has to be followed is the flatness of the parts. So what we're talking about is across this surface. So make sure that there's not any warp or sinkage or sink marks, anything like that across there, because if we don't get even contact of the height of the energy director against the opposing parts, there could be weak welds or in some cases even leaks in those places. So a couple of different things for ultrasonic welding. We'll talk about some joint designs, different types of joint designs that we recommend, but then we'll also talk a little bit about some alternate ways of using ultrasonics for either forming, inserting, or embedding. These are what we refer to as our preferred joint designs, and then from left to right here we have the step joint, the energy director with tongue and groove, our mash or shear joint, and then for thin-walled parts, the double V joint. We've seen joint designs such as these, which are the basic energy director, the 45-degree shear, and a flat-to-flat shear. We don't recommend these types of joints. We have seen them in the field quite often, and we'll go into why we deem them as being problematic. So let's look at the individual joint designs here. This is the energy director with step joint. So think back to the 7 points that we talked about earlier. Having a sharp point to initiate the contact, having sonotrode input, fixturing this part very well, not allowing the parts to bottom out. So this dimension should be taller than this dimension. And then with the step joint specifically, what you'll notice is that the energy director is not centered on this wall, but rather pushed to one side. We want the melt to be in contact with as many surfaces as it possibly can. If the energy director is centered, or if it's moved to the opposite side, what would typically happen is that we would see some of this melt kind of come out and possibly break off and get into an undesirable area. So for that reason, we recommend that you move it closer to an adjoining wall or a vertical wall so that the melt can be contained and then aid in the strength as well. Here's an example of an energy director on a part that we welded. So you can see that this is a rather small part, and for that reason, the shape of the energy director is in the 60-degree configuration. So before welding and after welding, you can see that the melt was contained and that we have a nice solid bond between those two surfaces, an almost imperceivable line between the two parts that were welded. This is a variation on that step joint. So again, if you have very thin walls, it's okay to somewhat modify the shape of the energy director. Again, keeping it pushed over to an adjacent wall so that the melt is contained. And again, just pay particular attention to leaving a bit of a gap in between the parts so that they don't bottom out, or that these two surfaces do not come in contact, that the welder should control any sort of gap that's left over. On the previous slide, as well as on this slide, we showed these ribs. If you have issues with centering the part, ribs can be added perpendicular and in this configuration along here to make sure that the blue part is centered within the red part. So that's what these graphics on this slide and the previous slide were showing. The energy director tongue and groove is really the go-to. This is, whenever possible, the primary recommendation that we make. So you'll notice that the the tongue is fully contained within the groove, that the melt now not only bonds on 2 surfaces, but hopefully bonds on 3 surfaces. So mechanically, there's an advantage. The disadvantage, of course, is that the wall thickness of this part ends up being wider than you may be able to tolerate. But whenever possible, if you can fit the tongue and groove energy director into your design, this is really the go-to. And as I mentioned, having some clearance between the parts. Again, they should not press fit together, but they should be loose, allowing the red part to vibrate in phase with the sonotrode, and allowing the blue part to remain motionless in the fixture. It gives the melt a place to go and fill into, but again, allows this part to vibrate freely together with the sonotrode. In some cases, especially for semi-crystalline materials, we've developed the mash joint. It's a variation on what you may have seen from a typical shear joint. So what we've done is to add a slight angle here. In the more traditional shear joint, this would be a flat area, and therefore it does not allow point contact. So again, initiating the melt with point contact is a requirement. And what we see after the welding is that the melt is contained within the parts. We still get that shearing effect of the red part into the blue part, but the angle is what's important to note here. And here's an actual part that has been welded with the shear joint, the mash joint. So you can see, even though these parts are of different colors, the bond line in the area, there's an imperceivable bond that's developed there, and then any flash that is created flows and is contained within the part itself. So for thin walled parts, the joint design that we recommend is the double V. So here we have 2 points of contact. Again, minimizing the surface area is what's required. But in this case, because of the typical thin walls that we see, the double V joint allows for the flash containment within the melt area, and also has the advantage of working well with thin walled parts. So you can see here an example of a double V joint, 2 points of contact, flash containment within the V, and then after welding, you can see that it's a nice solid weld, leak-free weld can be created. There are cases where the ultrasonic welding can be used only for mechanical attachment of the parts, and an additional seal ring, O-ring, valve, whatever it might be, is what provides the actual seal. So in these cases, higher forces are typically required, but again, the bond is intended to only hold the parts together, and then the seal is created by that O-ring or that valve. When designing your parts and you have a corner that you have to negotiate around, we do not recommend that the energy director be squared off. The energy director should be radiused, or if it's just a mechanical bond that you're looking for, eliminating that corner or 90-degree shape is preferable. Reason being is that in the corner here, an overabundance of melt is created, and that overabundance of melt can sometimes cause you to underweld the part, or if you do overweld the part, then that overabundance of flash usually doesn't have anywhere to go, so it is visible on the outside of the part. Another technique for mechanical joints, not leak-free joints, of course, is to segment the energy director. So instead of a continuous energy director going all the way around, a segmented energy director can be the solution if you just need a mechanical bonding of the parts. So quickly turning to some of the trouble designs. And again, if you think back to the 7 points that we want to achieve, the biggest problem here is that there is no melt encapsulation. We only have one surface to bond to, and then depending on how much the weld depth is programmed for, you may see flash coming out. The parts do not self-align, so this may have to be done with either the sonotrode or the fixture, which is not recommended. But for those reasons, we typically do not recommend just a basic energy design like this one. Moving on to the 45-degree shear. So there are some considerations that have been given. So we do have the point contact. This angle here and the squared off edge of the red part do provide point contact. So we do start the melt very effectively. The problem becomes in dimensional tolerancing. So imagine if the blue part were a little bit larger, or the red part were a little bit smaller, or in the worst case, both the blue part is larger and the red part is smaller. The interface, instead of being here, will move down to this area. So therefore it reduces the amount of collapse that you can put into the part. So for dimensional issues, we don't recommend this shear joint, but rather our mash joint, where this angle then would be inverted. No melt encapsulation as well. So very often in a typical shear joint, we do see loose flash being directed to this side of the weld. It's very difficult to get the melt to kind of move up into that area. So again, for those reasons, we typically do not recommend this 45-degree shear. Additionally, the flat to flat shear. So those dimensional tolerances are taken care of. If the blue part were larger and the red part were smaller, we still have contact between them, and it doesn't change the weld depth, but it does change the volume that potentially could be generated through the melt. So a smaller red part or a larger blue part will change the amount of interference between the parts. So dimensionally, you have to pay attention to that. And again, melt encapsulation ends up being a problem as well. So moving on to some alternate joining methods, swaging, staking, and spot welding. These are instances where an energy director is not utilized or not molded into the parts. And often the melt initiation is done through a detail in the face of the sonotrode. So in the case of swaging, we're reforming a wall to capture a dissimilar material. In this case, the green part can be a piece of steel, a piece of glass, a printed circuit board, something that is not weldable. Also, in this case here, the green part can be a piece of steel or a circuit board or something, and the sonotrode has a detail in it to reform a post. So the biggest difference between swaging and staking is we are either reforming a wall in the case of swaging, or we're reforming a post in the case of staking. Ultrasonic spot welding uses a sonotrode that has a detail in it that pierces through one of the parts and halfway through the second part. So the material that is displaced from the red part and the material that is displaced and melted from the blue part mix together, and then they fill in between the parts, and that's where the bond happens. This results in a sort of rivet head being seen after the welding, and it's often done on thermoformed parts or parts that you cannot usually weld with an energy director. or very large parts that don't require a full perimeter seal, but rather might just require some spots to be welded. So as I mentioned, in swaging, the wall is reformed. So here we have the before picture and the after picture. So calculating the volume of the plastic and comparing it to the volume of the sonotrode is very critical. Making sure that after welding, the melt that was created doesn't flow outside of the containment area. Another consideration is that certain glass-filled resins, I mentioned earlier that glass is can lead to wear. It's abrasive. So having this glass-filled material in direct contact with the sonotrode very often results in wear of the sonotrode. Wear of the sonotrode then results in a larger volume. So therefore, you may not get as tight of a swage as you would have experienced previously or earlier in the production process. So it's something that has to be considered. We can use steel sonotrodes. We can use a coating on the sonotrode, but the melt volume calculation is quite critical in this case. Staking hollow posts. We'll see this often in automotive applications for map pockets, door handles, door pulls, those kinds of things. Multiple components in automotive door panels are assembled with a hollow post coming up through the other part. The sonotrode again has this melt volume that has to be contained. So before welding, you see the post rather tall, and then after welding, the post is melted, reformed, and then very tightly holds the dissimilar material. Again, wear of the sonotrode, especially for glass-filled materials, is a consideration here. Staking of solid posts, we have a little bit more flexibility here, and you can see the different designs that we can use, anything from a low-profile dome to a knurl or just a flat. So again, the detail is in the sonotrode. There's no joint design, there's no energy director here. The point of the sonotrode acts to initiate the melt, and again, melt volume encapsulation is quite critical. I briefly talked a little bit about spot welding previously, but again, no energy director here. The intent is that the sonotrode has the welding detail. So again, the sonotrode pierces through the first part that it contacts and goes halfway through into the second part that it contacts, and that displaced or molten material flows and causes the bond in between the two parts. Inserting is another common method that ultrasonics can be used for. So what we're talking about here are threaded brass inserts. So if your part requires disassembly, or if a threaded screw will not give the retention power of going directly into the plastic part, often threaded brass inserts are used, and they have these opposing flutes, these knurls, these undercuts that create a higher amount of retention force. So the sonotrode, again, hardened steel because we're making metal-to-metal contact. The sonotrode heats up the threaded brass insert, pushes it into the plastic part, and the plastic part's hole here is smaller in diameter than the size of the insert. And the intent is that the molten material of the plastic flows into and is contained or trapped within those flutes and cuts and knurls, and to provide the retention to accept a screw for disassembly. one more point just on here. I didn't mention about grills and meshes and screens. So if you do have a metal grill or a metal mesh that has to be embedded, that can also be done. The metal mesh would be contacted by the sonotrode and then pushed into or embedded into the plastic part. Embedding. So there's two different methods for embedding. We can either mold in an energy director, or again, use a detail in the face of the sonotrode to do the embedding. In both cases here, we're talking about a filter or some sort of fleece, a film maybe that would have to be attached to the sonotrode itself, or to the other part itself. So again, two different designs, one with an energy director and one with the sonotrode acting as the energy director. The thing to consider here is the thickness or the loft of the fleece or the film that you're using. If it's a very thin film, we typically do not recommend the energy director design, but rather would recommend the design where the sonotrode is doing the embedding. If it's very thin, what can happen sometimes is that the very thin film can be cut by that energy director. So in those cases, more often than not, we recommend that the sonotrode have the detail a larger surface to embed the film into the plastic part. Okay, we sorry to run over a little bit in some of the technical difficulties that we had previously, but that will conclude the design portion of the seminar, and I'd like to open it up to any questions that anyone might have.
Hey, Vasco, can you hear me?
Yes, I can.
I have captured some questions from the chat box. So
Okay.
I'm going to start with those, and then if folks want to continue to push them in there, that might be the easier way. If we can hear you over the phone, we're more than happy to do that, but we haven't had a lot of success with that. But let me start with these. So Matt asked,
I do see the chat here. Yeah, I see that Matt asked the question, is there a joint design that you prefer for hermetic seal or for a pressure vessel?
Mm-hmm.
Yes.
Mm-hmm.
So Matt, the number one go-to that we would recommend would be the tongue and groove energy director, followed by the step joint. So whenever we have the wall thickness that would accommodate a tongue and groove joint design, that would be the preferred design for a leak-free or a vessel that has to be created.
Okay.
Next question was from Ben, and he asked, what tolerance can you expect in the vertical direction if you're relying on the encoder of the welder as opposed to a hard stop on the part? So the encoder has a 10 micron resolution, so 0.01 millimeters. And that's the resolution that we typically use when bonding parts. We can see not only the RPN distance, or the distance that is achieved during vibration, but we can also measure the distance after the weld or after the vibrations have concluded. That molten material is further compressed and squeezed, and the part is still continuing to move until it solidifies. So with a 10 micron resolution, we find that that's pretty reliable for the majority of applications.
And then there's a question from Scott.
Okay.
I don't know if you see it or not. I have one. It might have come in on a private. How clean of a finish can you get with swaging? And it says ... cosmetic possible.
I would prefer not to have a cosmetic surface be swaged. There can be variability in the height of the part to be captured. So whenever possible, those types of swaging applications are for internal components more often than for cosmetic appearance. That's not to say that it can't be done. Each individual application is unique, but we'd have to review it further. But initially, my general response would be that swaging should be used for internal components, not typically for aesthetic or external appearance.
That makes sense. Mm-hmm. And then I have a question from Nick. I don't know if you see it there or not. It says, outside of allowing the welder/encoder to perform its intended function, are there additional factors which make the hard stop design not a best practice?
Not necessarily. I mean, the problem could be that if you have a part that has dimensional tolerancing such that it's smaller, and you use the hard stop to limit the travel of the sonotrode, you may be under welding that particular part simply because its dimensional tolerancing is a little bit smaller. And then depending on if you're welding by time, let's say, and you hit that hard stop and the part has been fully compressed, if the weld time hasn't been met, it will continue to vibrate on the part even after the part has bottomed out or the mechanical stop has been hit. So in those instances, if you over weld a part that has already met its bottom stop, the generator doesn't know that it's supposed to stop, so it'll continue vibrating and put an unnecessary or additional energy into the part, which could cause part damage.
Right. And then Marco asks, have we ever developed a peelable seal using ultrasonic welding, for example, a yogurt type package? Yeah,
this is very common. So we're divided up into 4 business units. I've previously been a part of the plastics division, which Ray is a part of. And so we normally deal with injection molded rigid plastic parts, but we also have a division that deals with packaging. We have a division that deals with metals, and we have a division that deals with nonwovens. So within the packaging division, they're dealing with peelable seals all the time, whether it's on a yogurt cup, whether it's on a coffee pod, whether it's on a Capri Sun juice pouch or other types of films that are being sealed. But yes, peelable seals are very common, but I would say that our packaging division is more suited to answering those questions in specifics than we're prepared to discuss here.
Yes, I will go ahead and connect you, Marco, with the folks there. I'll put that connection together for you. I'll take care of that. Are there any other questions? Okay, so once again, Bosco, I got some feedback, and it continues to be very good. One of the very good pieces of feedback is while we try to keep these at bite-sized chunks, that the the density of the information and the amount of time maybe are a little bit off, which I can appreciate. We were trying to make it more bite-sized, but we're trying to put basically a larger morsel into what is a bite-size. So it sounds like folks might be interested in seeing this type of presentation, maybe a little bit longer. Maybe it would be better if it were maybe a 90-minute or a 2-hour session, and just try to size the density of the material and maybe allow for a little bit more of an open Q&A once we get that technical aspect figured out. But that was really good feedback, and we appreciate that.
Yeah, and just to kind of echo that sentiment, Ray, this seminar is intended to go over about a 6-hour period. So
right.
The morning session, we did condense into about a 1 hour, and then this session we also condensed down into a 1 hour. I have and I might have missed the introduction. I don't know if you did the introduction, Ray, but so my experience, I draw on 25 plus years of experience, and I have quite a few stories to tell and quite a few examples to share. But for the sake of time, yes, unfortunately, we had to leave some of those stories out or condense the information as needed. So I would just say that if you have some questions that haven't been answered, or you have some concerns or lingering topics that you might want to discuss further, we're always available for individual consultation afterwards.
Right, that's true. And if there are recommendations, if you think a 2-hour would be something that folks would be interested in, we actually have a group that's doing looks like a half-day session where they're going through maybe a more traditional, run through. So, those are things that we're open to as well. So if there are no more questions. Yeah, and absolutely.
Just one last thing. A lot of this has to do with getting your hands on the welder as well. And as you can see from the agenda, the next component of the training is to actually set up an ultrasonic welder. So for those of you that maybe are designers, this may have been a good initial introduction, but getting your hands on the welder and learning through touching and doing and seeing certainly has its advantages as well.
That's right. And so we do have the traditional full-day technical seminar that we have at U Lowell. You guys will usually get a invite to that. I think it's about $275, and we cover all this material and the hands-on together. I kind of liken it to the fact that Bosco is sort of our Jedi, and you don't become a Jedi on one day of training, but you could become a brown belt, and that's not so bad for one day's worth of investment. So I'm going to go ahead and finish here and say thank you to everybody. We appreciate it. Stay safe out there. Take care of yourselves, and I'll continue to post some additional information. If folks are interested, they can participate in the future. Thank you, Bosco. Really appreciate it. This was very successful.
My pleasure. You're welcome.
Bye, everyone.
Okay, thank you.